Brink team, it's great to be here. Thank you so much for the invite, especially Gloria and Fanquake. Yeah, looking forward to presenting more about. I'll get started with myself, Alpen Labs, little bit of intro, and then I want to talk more about Strata, which is what we're building and sort of why we're building it, and highlight some of the use cases. Let's see. And happy Valentine's Day to everyone. I threw in a couple of hearts here because it's Valentine's Day. So yeah, just as an overview of some of the stuff that I want to talk about today. I'll get started just telling you more about this Alpen Labs. Why do we even exist? And then want to go through Strata. I know that I think you guys had Robin Linus on sometime last year around BitVM. I think there's going to be some overlap with BitVM, so I won't go super deep into that, but I will kind of the latest of what's happening, and a lot has been happening on that front. I'll cover here. And I want to go through some concrete use cases, like why I think this is actually interesting, what this enables. And hopefully we'll have some time here to also chat about some of our ongoing research in privacy and covenants, and how that might even improve some of the systems that we're building. So I'll get started, yeah. So Alpen Labs, what is it? Who are we? We're a startup, about 30 people now, and we're really building scaling solutions at the intersection of Bitcoin and verifiable computing. So that's kind of how we think there's really two big ongoing revolutions here, and at the convergence, there's a lot of really unique opportunities to build really accessible payments and money solution, and we're really excited about that. So right in money, of course, it's Bitcoin. And we also, see in computing the idea of being able to generate proofs of arbitrary computation. This is getting so much better and has really crossed the chasm from theory to practice. And really excited about building solutions there. We worked a lot on a lot of our team worked on some of the earliest research on Bitcoin rollups. So Trey on our team, who's formerly at DCI, working on one of the earliest Lightning implementations, I think had the first kind of design spec out on what a Bitcoin ZK rollup might look like in early 2022. John Light wrote a report, I think, that was really kind of energized more folks in the space, and that was bitcoinrollups.org, so validity rollups on Bitcoin. And myself, one of the co-founders of Alpen Labs, along with some of the other co-founders, we were actually around that same time in 2022 working on, what this actually could look like, and a very concrete design of ZK rollups on Bitcoin, assuming a few new opcodes, but what that actually looks like with Taproot, and actually designing all the contracts and writing all the contracts. So these are some of the papers here. The team comes from a kind of background both in Bitcoin. So we have folks from Blockstream Research, like Liam Egan, and also come from, outside of Bitcoin. Our research engineering lead, led the implementation of Rollups Plus, and this is like one of the most widely used ZK protocols in production today, powers Monero. And why we're really excited about this intersection is, I think that's the next slide. Yeah, okay. I think the idea that, like, we basically bringing the best kind of privacy technologies, on-chain finance technologies to the best and biggest electronic cash is, I think, what is super compelling. And in doing so, we think we can really kind of expand the usage of and access to Bitcoin. So ability to kind of hold in self-custody, and also the user experience around that, and more things that you can do with Bitcoin without having to give up custody and kind of sacrifice core properties. this is what we're interested in, and we're focused in building kind of at this intersection of Bitcoin and verifiable compute, a new type of expressive scalable layer 2 solution on Bitcoin, with kind of a looser definition on layer 2. We'll talk about that more. And yeah, basically, we're after a couple of years of research and development, really excited to be launching Strata into mainnet later this year, which is a ton of work going into it. So how does this work? I mean, what am I talking about in terms of like the intersection of verifiable compute and Bitcoin? Well, SNARKs are not like really new, particularly new in the Bitcoin world. I think I pulled some of these quotes from Greg Maxwell and Bitcoin forums like 2016, I think, and there were references even earlier. I think there's this recognition here that blockchains are really systems that should be designed to do verification, not computation. And if we want kind of more expressivity that's too limited with Bitcoin script today, these can be built, but it doesn't mean that we need to make script super expressive. We just need it to be expressive enough to be able to verify SNARKs. And at the time, it was mentioned, SNARKs is something that we could actually do, but this is about a decade ago, and just generating a proof of basic signature validation or any basic programs, it was really, really slow. The proof size was relatively small, I mean, depending on what kind of system that you're using, but being able to actually generate the proof was very difficult. And this, SNARKs kind of presents this really nice asymmetry in computation, right? Where you can take, arbitrarily sort of complex programs, and it is just kind of this universal abstraction for, which is a proof for being able to validate the integrity of that program. So rather than having to execute all of that program, you can, in a very constrained environment like Bitcoin scripting, be able to know the integrity and validity of that program execution without having to like actually execute it. You can actually just verify it in much simpler way. And this is a very powerful kind of universal primitive. Yeah, so the most important thing here is that verifiable compute is now very practical. We have a bunch of options we can take, fully sort of hash-based, even SNARKs, STARKs, as they're called. We have folding schemes, we have bulletproofs, and various options to choose from. And what's really interesting as well is that it's like not only kind of cross that chasm from theory to practice, but also that there's incredible tooling built around it where you can take arbitrary Rust program today, and there are multiple ZKVMs. ZKVMs are RISC-V compatible front ends for a SNARK prover. So you can basically compile and run your Rust program in this ZKVM, which in turn generates a proof of the validity of that execution for you. And it is something that we're doing, today in our systems. I've run these provers on my laptop, and it's fast enough to like really, on testnet today in Bitcoin, we're able to actually run tremendous number of transactions on our layer 2s, prove that, and generate about a fixed size, about 200 byte proof attesting to all of that computation. I see there's a question from Frank. Yeah.
Just for some context, when you say fast enough, like what do you mean? Are we talking seconds, like tens of seconds, milliseconds? Like,
yeah, so I guess there's two parts to this of generating a proof and verifying a proof, right? Yeah, proving and verifying are the two. Verifying, I can verify SNARKs on my phone basically in a matter of tens to hundreds of milliseconds. Um, and in this is like with the Groth 16 proof, like the claim that is being proven, the program that is being proven is could be arbitrarily large, but there's fixed size proof for that. To generate the proof, what we typically do is actually use a Stark based system, which is it's the fastest kind of way to generate proofs today. We actually wrap that. You can recurse on SNARKs as well, so you can verify the Stark as a computation, and then generate a SNARK Groth 16 kind of proof for that as well, which is you just make the Stark proof much smaller. So that's the kind of interface that we have. But yeah, proving is when I say fast enough, I mean we're able to basically horizontally scale our prover and like I think prove I don't have concrete metrics on this, but like thousands to tens of thousands of transactions while posting proofs on Bitcoin every few blocks, every I think 10 blocks is how we do it. But I think by the end of the year we expect basically to have proofs be posted every 10 minutes and be able to verify thousands of transactions and be completely not have to like basically be in sync with Bitcoin. Yeah. And what's kind of neat about the SNARK and this kind of universal abstraction for verifying arbitrary computation is that it is a very important building block. If like Bitcoin can reason about a SNARK somehow, then we can we're much closer to building this trustless two-way peg approach, which is allowing someone to be able to deposit into a contract on Bitcoin, and that gets minted on a side chain, or for actually a trustless two-way peg, you'd want something like a rollup, and then be able to unilaterally withdraw BTC. So basically being able to move BTC to and from arbitrary kind of expressive layers. This is something that if we can verify and Bitcoin can, if we can reason about a validity of a SNARK on Bitcoin, we can reason about validity of arbitrary computation, which means we can be able to reason about the state of another expressive layer on Bitcoin, and really do this like a trust minimized two-way peg. That opens a lot of doors in terms of being able to use BTC really securely within smart contract environments, or really any kind of arbitrary environments, whether it's like a simplicity layer 2 or even like a shielded CSV peer-to-peer payments kind of protocol. The ability to take Bitcoin and bring it to these meta protocols, that's like a really compelling application. It's the bridge. And then today it is, I'm going to kind of present a little bit on this. It's possible to verify a SNARK on Bitcoin through this one-round interactive protocol. This is based on BitVM2. That too, we feel has crossed from the chasm of theory to practice, and we're, ready to kind of bring this into production, in a matter of months. And then, with like some very deep audits and security proofs, we hope to bring this into production onto mainnet later this year. And the one round interactive protocol, with sort of that means is essentially someone can make a claim about a SNARK on Bitcoin. There's the BitVM2 protocol allows for someone to make a claim about the correctness of some arbitrary computation, and in a permissionless way, anyone can challenge that claim, forcing the claimant, the person making the claim, uh, to be able to post certain kinds of bit commitments on the chain, which essentially leads to, if the claim was actually right, if their claim was right, then they're fine. If the claim was wrong, someone is able to spend from a taproot address, basically, which is the claim. So essentially, it allows someone to make a claim on Bitcoin, and if that claim is wrong, anyone is able to slash them in this one round interactive protocol. And it's a claim about validity of a snark, which is, we'll unpack that a little bit. And we use this primitive actually to build out a bridge, and we can build a one of n trust minimized two-way peg. And so what do I mean by the one of n? For building, so you think of the bridge as sort of an application of this ability to verify snark through a one round interactive protocol. Like, we can do a bunch of things with that. One thing is we can build this kind of bridge, but the bridge requires more than just that, right? Like the bridge requires some way of being able to hold deposits into a UTXO, and without covenants today, we have to emulate that through an n of n holding those deposits, and this is where the one of n trust assumption also comes into those deposits. So like if you're putting a bunch of deposits into UTXO or different UTXOs, those are held by n of n, and essentially those deposits, by putting it into a deposit contract on Bitcoin, a side system like a rollup is able to mint that one Bitcoin. And the whole protocol, the bridge protocol, is about how do we ensure a one-to-one peg. So when in the side system, your BTC that's there, you burn it, you should be able to retrieve the BTC from the deposit contract on Bitcoin, and this must maintain a one-to-one peg. That's very important. So the one of n trust assumption essentially comes from the contract that is holding the deposits on Bitcoin side is a n of n multi-sig contract. And we do this because there's a way to sort of emulate covenants with connector outputs and this kind of n of n contract. And this is like actually quite interesting because the best way we can kind of do trust minimize two-way pegs today are like really wrapped solutions, or like 2 of 3 majority multi-sig assumptions, or just trusting a custodian fully, like with CBBTC, you trust Coinbase, and they just facilitate the deposits and withdrawals between Bitcoin and Base, which is another blockchain. So getting this down to a one of n trust assumption is a pretty big deal, especially if you can include a bunch of other entities, and only one of those entities has to be honest for that deposit contract to not be spent somewhere that shouldn't be spent. Yeah. So I want to go through how I think about I talked about rollups here, sovereign rollups, maybe NCK rollups, and so on. So I just want to go through quickly about what those mean, what is a sovereign rollup, etc. And I think this is a framing. I think that could be helpful. So and maybe this beginning part is something that maybe we're already familiar with. I'm sure most folks here already understand this, but this is the framing that I want to set, which is let's think about Bitcoin as a state machine for now. The state is the UTXO set, and each time a new block is proposed, basically we're running this state transition function. We being like a Bitcoin node is running this state transition function where given the UTXO set and given this new block as inputs, the state transition function is basically a program that validates every transaction in that block, and it updates the UTXO set. So the output of that is, if everything is valid, if the block is, if it follows all the rules that is set in protocol, the output should be the new UTXO set. And today, essentially, a Bitcoin node is running state transition function, and it is running also the fork choice rule, which is that's sort of like the consensus protocol, right? That's a proof of work piece, which is amongst several different competing chains or different blocks, like we need to have a deterministic way of having consensus on what is the canonical state. And so this in Bitcoin, of course, is choosing the highest cumulative proof of work. And what a sovereign ZK rollup is now kind of, on that framing is we can think of a sovereign ZK rollup initially just as a meta protocol. Think of it as a meta protocol on Bitcoin where, there are block producers for this. And let's say consider the sovereign ZK rollup as it's running, let's say, EVM account-based style, a completely different, execution environment, and state model is like Merkle tree account-based kind of state model. Let's say it's something completely different from the UTXO Bitcoin script approach. So this is another blockchain essentially, but it's also a meta protocol on Bitcoin in that there are block producers for this sovereign ZK rollup. We call them sequencers, or they could even just be one sequencer. And these sequencers basically execute all of the transactions, that are made in this, and produce a validity proof attesting to the correctness of all of the transactions. They compress all the transactions, so if basically we just need diffs of those transactions and post these on Bitcoin. A rollup node in this scenario is actually just running Bitcoin. So they're doing, verifying the state transition function, fork choice rule of Bitcoin. And on top of that, they look at the data that is being published on Bitcoin, and client side, they are able to verify state transition function and FCR of the rollup. And so they arrive at the latest state of the rollup through data that is available on Bitcoin. And what's neat here is also that because validity proofs are being posted, in theory they don't even need to be posted, the validity proofs. You could just post state diffs on Bitcoin. And because posting kind of validity proofs on Bitcoin, very small proofs that are posted, these rollup nodes can actually instantly sync, and these are actually recursive validity proofs too. So basically a rollup node that wants to get to the latest state of the rollup, they'll run Bitcoin, they'll verify the latest state on Bitcoin, and look at the latest kind of state, latest valid proof and state published by the block producer on Bitcoin, and they can immediately verify this validity proof client side, and get to the latest state of what the rollup is. And if they're a full node, they can also given all the state diffs, they can basically create what the full state is as well of the rollup. And so the advantages this has is, of this kind of setup is that basically rollups can be reorged if and only if the base layer is reorged. So they inherit double spend security of Bitcoin. Because the state, of the rollup is derived from the state of Bitcoin alongside additional kind of steps that's done there. So to be able to double spend any transaction on the rollup, you'd have to double spend on Bitcoin. And there's also flexibility in terms of being able to do a hard fork, for the sovereign rollup as well. In that, like there could be a social fork on the rollup that changes what fork choice rule might look like, and people can update their node for how to derive kind of that fork choice rule. And basically you can have a social fork that happens on the rollup, or a hard fork that happens on the rollup. It is not essentially enshrined by Bitcoin, right? Like Bitcoin, like for a hard fork to happen on the rollup, it's not the case that like a hard fork needs to happen kind of on Bitcoin. And another thing that's sort of neat about this approach is that like you can have whatever kind of execution environment you want on the ZK rollup. It doesn't have to be necessarily a UTXO based thing. It doesn't have to be it could be a UTXO based thing with even new opcodes if you want, etc. So this is like generally the concept of a sovereign ZK rollup. Think about it as a meta protocol, because we also haven't discussed how does this roll up this get access to BTC, which I think is like the most interesting part, right? So this is like the two-way peg. So far we've sort of outlined, hey, here's this meta protocol where nodes can be running Bitcoin nodes and then do additional steps and arrive at consensus of this. But maybe that's interesting. It's like I don't know, like stablecoin assets can be traded or something like that, and sort of settled through Bitcoin, in that like the security still inherits of Bitcoin. But I think where this actually gets interesting is unlocking BTC into these kinds of environments. And so this is where the two-way peg is like a really interesting part of the design. And as we talked about with SNARKs earlier, it's, if a Bitcoin script can verify a SNARK, then it should be able to verify the state transition function and fork choice rule of Strata. I guess I didn't introduce Strata here, but Strata is a ZK rollup, using what we call optimistic ZK bridge, which is this BitVM2 style of bridging for Bitcoin. So it is, expressive layer 2 on Bitcoin that allows BTC to move in and out, and it's expressive in that it is a smart contract layer where folks can build things that they couldn't build on Bitcoin, and at a more scale as well. So if we talked about basically what the role of a rollup node is, and essentially what we need to do to build this like two-way peg into the rollup is have Bitcoin script, like the capability of Bitcoin script, to be able to verify, essentially like run a light node of the rollup. Kind of meta, but like the idea is that if Bitcoin can reason about the latest state of the rollup, then it would be able to unlock the deposit back to a user, seeing that maybe that BTC on the rollup was burned and initiated for a withdrawal, right? So like if Bitcoin script can reason about the state transition function and fork choice rule of Strata, and the state transition function of Bitcoin, we definitely would have a lot more capability towards actual light node within script, right? And so this is kind of the role of a snark, right? You can actually, as long as in Bitcoin script you can reason about a snark, like this, the rest of this stuff is just computation. And it's just a program, and it should be able to reason about that. One thing though that is very tricky, and it's something that we're actively there are different kind of approaches to this, and even these BitVM2 style bridges are actually a little bit different. A subtle point here is that while you can reason about like state transition function and fortress rule of the rollup and the state transition function of Bitcoin, these are just programs that can be run. How do you know, a claim is being made on the canonical Bitcoin chain, right? Like that's a more subjective thing where what if a valid claim about, all of this was being made on a private fork of Bitcoin that's not the canonical chain? Maybe the proof would be correct, but you also need to, in order to, for the bridge to be able to unlock funds, in the canonical chain, you need to have some way of verifying that the SNARK proof is actually valid over the canonical Bitcoin chain. And this is tricky because we don't have things like OP, block hash or something like that, or some way of block introspection or statefulness is not really possible. I mean, very limited amounts are possible, and we are absolutely taking, being creative around how that's done. For example, like with being able to introspect to some degree about the time, right? From script through check lock time verify or these kinds of opcodes. This is definitely an important part of how we design the second part, which is SNARK proof being valid over the canonical Bitcoin chain. So I didn't really want to go super deep into like BitVM2 and how that works and whatnot, because this has already been a presentation. But I did want to highlight that there's just been tremendous progress happening on that front in terms of getting it to be closer and closer to being production ready. This is a theoretical concept that came out like last year. It followed BitVM1, which is a really kind of neat concept, but seemed highly impractical to actually build things like bridges in production. It was a multi-round kind of interactive protocol. I think it was something like 40 rounds to be able to adjudicate, the validity of some kind of computation, doing like this whole bisection protocol. And what that translated to was basically if each round, for liveness reasons is like a 1 week or something like that, it would have meant like in the worst case, like someone's trying to do a withdrawal from the rollup back to BTC, and it's like they're challenged, and this challenge period is like, I don't know, like 40 weeks or something like that. That was BitVM1. That was very early. Of course, like there's been innovations on that. From Alpen, we'd been working on what was called Snarknado, named after the amazing movie Sharknado, which was instead of trying to do this bisection on like a RISC-V trace, we were doing it directly on the SNARK, and that got it to 4 rounds. But then this is also last year. Then BitVM2 came, which is a really neat concept of, hey, like basically we can do this in 1 round, and at a high level, the Groth16 proof, which is a SNARK proof itself, is very small. It's a couple hundred bytes. But the verifier that's written in Bitcoin with all the limitations of Bitcoin scripting was actually closer to like 5 gigabytes or 5 to 10 gigabytes at that time, and it's gone down considerably. But still, like this is way too big, right? 780 megabytes is very, very large. It's like it's not going to fit in a block. It's too large. And the idea was, hey, like we can split this entire verifier into a bunch of subscripts, a bunch of chunks, as we call them, and be able to, as if the verifier failed, meaning the proof is invalid, then, and we broke, this giant 780 megabyte proof into a bunch of chunks, a bunch of pieces, then at least one of those pieces must also be invalid. That was kind of the idea. and we could put all of those on in a tap script tree. So like each chunk, each piece of this entire 780 megabyte program could be in one leaf, and someone to disprove, the proof or invalidate the proof, they would just need to spend one of those leaves, and one of those leaves is considerably smaller. So you never have to bring the whole kind of verifier on chain. Just put it in Taproot. That was kind of the key idea. Yeah, Gloria.
Oh yeah, so can you hear me, by the way?
Yep.
Okay. So when you say progress for BitVM 2, like, is this the product of just kind of refining the design for how you would build this verifier within the confines of Bitcoin script? And then when you're thinking about potential consensus changes to
Mhm.
enable things, is it just from a size perspective? Like if you have like, I don't know, opzkp, and
Mhm.
it becomes just like a single opcode,
Mhm.
obviously I can see why that would be smaller, but like what are the nuances to what additionally you get with, I don't know, upcat or whatever
Mhm.
kind of different flavors of expressivity in
Mhm.
script. And then also, sorry if this is too long of a question, um, but my understanding is there's like the expressivity component, and then you also mentioned the introspection component. I would
Mhm.
imagine that having access to more block data is like a much bigger impact in terms of like the new things that you get. At least this is kind of like how I think about it in my head. Whereas the
Mhm.
trade-offs for size are a little bit less, I don't know, unlocky. Is that like the kind of right mental
Mhm.
model to group it into these two different things?
Mhm. When you say less unlucky, you mean like unlocking like improvements to this protocol, or are you talking about like all the kinds of things that get unlocked? What people can do with Bitcoin.
Yeah, I guess I'm wondering like if you have like state, which is a
Mhm.
very abstract term, but like
Mhm.
how how much, what kinds of crazy stuff becomes unlocked, just concretely.
Mhm. Yeah. I think okay. So there are a couple parts to your question. I think that
Sorry. Yeah.
yeah. So I'm trying to remember all parts, but like um the with something like cat or new opcodes, I think that actually comes like that's the most useful part. Of course, I think we can reduce probably this down further. Although I think there's some like pretty good numbers already here. We're feeling pretty good about as a sort of this one round interactive optimistic kind of protocol. Ideally, we don't even want it to be an optimistic protocol. Ideally, we'd be able to verify the SNARK or Stark, what the the proof directly in a single script. Right now, we have to write that in script, and there's no OP-mol or anything like that. There's everything is 32 bits, etc. So we have to get creative, and we're constantly making optimizations. And this is still down to 780 megabytes, right? I think definitely an order of magnitude, maybe close to 2 orders of magnitude over the last 6 to 9 months of improvements on this size here. I think, but we're plateauing. We're plateauing hard, but the idea is like we can split this and we can do this optimistic protocol, which then brings overall the size of this down quite a bit. Um, but yeah, any new opcode that would be helpful for size. But I think the most helpful thing would actually be to remove this one of n kind of assumption. Like we don't really want to emulate covenants with connector outputs. Like, this is fine, but it does add much more complexity in our bridging protocol, and also the trust assumption, right? Like ideally, we can even do away with having an n of n multisig hold the UTXOs, and actually, it's just a contract that is able to lock unlock those funds. So like a covenant based system instead of an event based system. So I think that's actually where the impact will be more felt with any kind of say OPCAT or whatever else. I think we have some opinions around like what might be interesting, what might not be interesting, but yeah. And then also the other thing with OPCAT, what I think is quite interesting is right now we are using this type of zero knowledge proof called Groth16. This is a SNARK based system. Ideally, there are purely hash based systems that like you just rely on the pretty good trust assumptions just around the around hashes, not even like kind of additional kind of elliptic curve or discrete log assumptions there, but verifying a Stark is actually quite straightforward. It is a bunch of Merkle verifications essentially. And so if we had cat, I think we would probably look towards a different type of proof system. That said, it's Groth16 does have some benefits like fixed size proof. It's a couple hundred bytes, no matter how big the computation is that it's attesting to. So while the scaling property is a bit different for Starks, so that's what I would say in terms of like the unlocks that come. And then Gloria, can you remind me what the second part of your question was? Or if I didn't cover something.
Yeah, I think you definitely covered most of it. And then I think it's more the first part of my question where I was wondering where, like when you say you've made a lot of improvements to the size and you're plateauing, like where do those improvements come from? I imagine it's just kind of like refinement over the process of like engineering it and fleshing it out and figuring out like what you can reduce, compact.
Totally, yeah. I think it's some combination of engineering and then also like research. So like this was a really, really cool paper that played a big part in a lot of the reductions that Liam Egan worked on proving pairings. He sort of took the idea that like verification is cheaper than execution to the extreme, where like we were able to redesign some parts of how a Groth16 proof even gets verified. In the verifier program, it was like executing some things that like actually could be just replaced with verifying, plus hints or something like that. And so there's a bunch of like clever cryptographic kind of tricks and things that get translated into engineering. And so like I would check out like in the BitVM, like some of the recent pull requests. It's like really cool stuff. Some combination of math and performance optimization that's been going on, and it's not just, I would say, from Alpen Labs team. We're working on some of the core research and definitely contributing on the implementation side, but there's a bunch of teams kind of across the world that are just like day in day out trying to optimize this further and further. But I'd say in these numbers we've actually reached like this is something that we feel pretty good about going into production with. I think we've crossed the chasm of like, this is still theoretical to like, I could see, how this works. And so I want to give very quick context on like what these other numbers even mean. I think some of this was maybe talked about in the BitVM call that you guys did. But yeah, so like if we just like had like this verifier, it's written in Bitcoin and like, 32-bit ads and things like that. Like, of course, we need to do field multiplication. We have a whole paper and implementation around how do you do like really optimal kind of field multiplication in Bitcoin script and so on. But like we basically can get the entire Groth16 verifier program down to 780 megabytes today. And as I mentioned, like we split this across in a taproot like a TapScript tree. We split this program basically into a bunch of chunks. And the idea is that like, given the input, one chunk computes some of it, and then takes the the input to the output, and then the output is part of the input for the next chunk, and so on. So these chunks need to be connected somehow, right? Like there's intermediate like progress that's being made on the program, and there's sort of intermediate states that need to get passed between each of these taproot leaves. These states are just hashes, actually. So turns out you can just like the thing that you're passing in between is just the hashes, and you can provide hints in order to verify the hash and so on. So like that's the most optimal way to do it. And so what it comes down to is when someone makes a claim about the proof, they present the proof, and essentially what they're doing is constructing this pay to taproot transaction in which they need to put into Bitcoin, they need to commit into Bitcoin all of the intermediate hashes of like that connect all of these taproot leaves. And so they're making a claim about like for each of these, like you can kind of bring this input in each of the tap leaves. You can bring this input in, and it'll result in this output, and they've bit committed to that. So the idea is that if any part of their, if their proof is invalid, one of these chunks must be invalid, and basically someone, and actually it could be anyone, can spend from this pay to TypeScript address, can spend one of these leaves, given all the intermediate hashes have been bit committed, by showing that, hey, this execution actually fails. And so they just need to spend one part of that 780 megabytes in order to invalidate the claim. And what the person who's claiming this needs to put on chain is all these intermediate hashes, which comes out to be about 426. I don't know why I included the .444, but about 426 kilobytes. And to be clear, like it's not like every time something, like when we apply this into building a bridge, it's not like anytime there's like a withdrawal of BTC from the rollup back to Bitcoin, like someone has to put like all that into Bitcoin. That this rarely happens. The idea is that like when someone's withdrawing, there's an operator. There's actually a set of operators here. They front the BTC to the user, and then they get a reimbursement from the bridge contract for that. And so they'll make a claim that, hey, I there's a valid kind of withdrawal here. I funded the user. I'm looking for a reimbursement, and there's a window to challenge that claim. The claim is not a SNARK at this point. It's just a claim that like, pointing to some transactions that have taken place on Bitcoin. And if there's something suspicious about that, like anyone can challenge it through like a very small, challenge transaction, like super small transaction. And only in the case of a challenge do they have to actually assert, put 426 kilobytes of bit commitments on Bitcoin, and then go through this whole, there's one assertion, and then once there's an assertion, someone can disprove, or maybe no one can disprove, in which case they get their reimbursement. So what I mean to say is, in the bridge application, we expect challenges to be super rare, cost money to challenge, and so when a challenge does happen, then these things get activated. But even in that scenario, this is like within the realm of practical, is what I mean to say. Yeah. And then the other thing to highlight here is like truly it's going down quite a lot, and it's like really neat to see. Like actually, in just as context, exactly a month ago, this number was, I think, about 1 gigabytes. So now it's down to 780, and that was pretty neat. And this was like closer to 560 or something like that. Yeah, Gloria.
That's really interesting. Wait, so when you're describing this optimistic kind of paradigm, this would be as opposed to like they directly publish, I don't know if it would be called an assertion, like along with their claim for the reimbursement, that is the proof. And then like there's no challenge. It's just like you verify that they're correct. Is that right?
What I'm saying is the use case of this BPM2 is in the context of this bridge, and particularly when you're withdrawing funds, right? Like, so you deposit funds into this NFN contract, right? And then that gets minted on the rollup, and then you're ready to withdraw it. And so the user basically burns that on the rollup, right? So that happens. The state is updated on the rollup and it's finalized through Bitcoin, showing that like, hey, this is like, basically there's a initiation to withdraw it. And then there's a bunch of these operators, bridge operators, as we call them. One of them will see, okay, there's, 1 BTC or 10 BTC that's burned. The user basically, the operator fronts that to the user. And then the operator is able to reimburse themselves, from the deposit contracts that are held in Bitcoin, the BTC. And the way they do that is they make this claim that, there's like a couple of ways.
Yeah,
one is like all NFN is live, and then immediately just sends it to the operator. They all see it, but they don't need to post a SNARK or these TypeScript chunks. They don't even need to create a SNARK when they are trying to get a reimbursement in the non-challenge path, which is, we think 99.9% is like going to be the non-challenge path. They just point to the like state transition like that was posted, and the transaction in which they fronted the user,
right.
and initiate the challenge, right? Like there's some like details there, but essentially they don't have to create this proof until they're challenged.
Right. So you're describing what an optimistic one looks like. So like my question is, how does this change if it's not optimistic? Do you no longer have this operator who is publishing this and like the user directly publishes a proof, or is the operator still involved, but they do directly publish an assertion that, there's no challenge period in this case because it's not an optimistic thing. It's just like a direct, like, I don't really know. I don't really have the vocabulary for it. And I guess I'm wondering, like, you've characterized this as optimistic.
This is a great question.
Optimistic.
Yeah. So it's a great question. So I think the operator, the fact that there's like, some fixed set of operators, and they can be like permissionlessly challenged, whatever, right? Like by anyone and so on. But the whole idea of like fronting the user and then kind of using this optimistic setup to then like that actually comes not from the fact that this is an optimistic protocol, but the fact that we don't have covenants. We have to emulate covenants on Bitcoin. So what I mean is like there's this N of N, emulated covenants via like connector outputs sort of approach that we're taking, right? And so what that means is essentially like when the funds are deposited into the bridge contract, this is an N of N contract. You need to also like, because there's no covenants, like we need to basically have all of the possible routes to, withdraw those funds like at deposit time. Like meaning, there's, you need to like, you can't know who the recipient is, right, at the deposit time of like how, the Bitcoin might be withdrawn unless there's a fixed set of operators. So basically at the deposit time, there's a withdrawal like transaction graph kind of that's pre-signed for all the operators. And the pre-signed transaction graph basically just allows like, hey, this operator in the future, when, you can make a claim for a reimbursement and you can get this deposit back to yourself. And so because we don't have covenants, we have to like pre-sign these paths ahead of time, right? Like at the time when these deposit contracts are created, when some user deposits into the system, like you need a way to exit through these pre-sign approaches. Like that's why like we have to do this operator-based like, fronting and reimbursement approach. So it really comes from the fact that we have emulated covenants and not real covenants versus like you can still have an optimistic protocol without bridge operators. like where the user actually can make a claim. So in that scenario, yeah, like a user can directly basically, go try to spend from the deposit contract to, take some BTC out, and, someone can challenge. And if there's someone challenges, they'd have to like, produce this kind of like proof, whatever assertions. And so like, yeah, you can actually have a optimistic protocol without the operators, I believe. Yeah. Cool. This is the last slide, but I really did want to highlight a few of the use cases and why we're actually excited about it. Right? Like, I think there's an opportunity with more expressivity and programmability to like really radically improve the payment UX without having to rely on custodial kind of solutions. These things can be built, like today we're building Strata as like, the first like VM like execution domain that we're putting on there is an EVM based, accounts based one. And we have, a layout for how this actually can be multiple different execution domains, and, over time. But just focusing on, that, and what we, is called account abstraction or native account abstraction. These are some of the payment UX, that can be like improvements that can be had for BTC payments, which like, imagine, you're going into a coffee shop paying via, your wallet, but you don't want to have the user worry about transaction fees. Maybe the transaction fees are actually paid by the merchant, or any third party. For them, it's like very, it's $3. It's then, or, it's fixed number of BTC, then it should be that. And so you can do these kinds of things with more programmability, meta transactions via like account abstraction. And another thing is like maybe right now we're used to push style payments, but being able to do pull based payments is opens up another paradigm for authorizing subscriptions or recurring payments. And that's kind of the premise of account abstraction. The idea is that like you can hold your funds in this kind of account where you can have the account is basically itself a smart contract. So like, application, wallets or developers can basically build programmable kind of authorizations in how you hold in the account that you hold some funds, right? And so you can like, hey, like any kind of programmatic thing, right? Like one is like recurring payment for this address. I'm authorizing the ability to take some amount out once a month or something like that, and that's like really neat. So you can do streaming, utility bill, auto pay, whatever else it is, and not actually have to be there as if you've already authorized it once when doing the payment. That's pretty neat. And there are even other examples of how we can really take the payment UX and expand it a lot further than what we can do today on chain. Things like streaming payments, micropayments, these things can even be built because your authorization for those funds can be programmatic. And of course, that complexity needs to be handled at the wallet level, but the users can customize it to the extent that they want. You can even do conditional or escrow-based payments, which is really neat. Like transactions are programmed with certain conditions. After maybe like an Oracle like makes or Oracle network provides some kind of signal that's happening in the real world, or even like in a multi-party kind of setting, you can unlock transaction like funds after a certain condition is met. So this really kind of like opens up the landscape for kinds of things that would make BTC payments even more accessible, more user friendly, and just new functionality. And another like set of applications that I think is really interesting, worth looking at, is like Bitcoin backed loans. I mean, today these are some numbers that I pulled based on like 2024 last year. today, some of the options for folks that want to hold Bitcoin, but want liquidity, maybe they want to collateralize it and get like dollars to be able to spend, is pretty bleak in terms of like things happening outside of like DeFi kind of use cases, right? So like you can go do a custodial or collaborative kind of custody approaches, and these are great companies. I don't mean to like really call them out like that or something like that. These are great companies, but still, like, look at the rates. It's something like 50%, close to 50% loan to value, and the interest rates are pretty high, right? So like you can take a $10,000 dollars valued in Bitcoin and $5,000 of stables or dollars that you take out and at a fairly high interest rate, right? Compare this to some of the innovations that have been made on chain, right? Like there's like really considerable like innovations that are worth looking at. Like I think Aave is like one example, but Morpho, like in others, like in Morpho specifically, I think has a even kind of more interesting model around this. These are live. This is like securing close to $6 billion today. Morpho is launched on like Ethereum and Base as the two. And interestingly, some of the biggest like uses are actually more around Bitcoin. Like people want Bitcoin back borrowing, even though that it's in other chains. And the only options actually today on the custody side is like you have like things like WBTC, which are wrapped, 2 of 3 kind of multi-sig BTC that's minted onto those ecosystems. You have like Ethereum or Base, whatever else security is there. But the numbers are there in terms of like you have like really competitive, up to 86% loan to value, with interest rates being much lower, doing the same if not bigger volume than any existing solution, and it's transparent and a lot better. So the idea is like, can we even do better, right? Like right now, instead of relying on just a single custodian like Coinbase for CBBTC, or relying on like, BitGo or maybe Justin Sun, turns out like, for WBTC, can we get towards a trust minimized version of this BTC in a programmable ecosystem wherein, there can be Morpho, there can be various vaults, and allow these kinds of applications to be secured through Bitcoin, to be much more trust minimized, and at much better terms. Like these are efficiencies to be gained through on-chain applications, and I think these are some of the much more credible uses of programmable blockchains, right? Especially in DeFi, this is quite neat. So I hope to have a fourth column here pretty soon. When we go live, certainly like one of our goals is to be able to allow these kinds of financial tools without having, again, this like trust, fairly trusted kind of BTC wrapper. Right. And, something that I and a lot of folks on our team are also very excited about are like Bitcoin-backed stablecoins. Like this is a really neat idea. Of course, users want UX of like stables, like as a medium of exchange. The opportunity to have a stable coin that is backed by Bitcoin presents itself as also a lending kind of solution, but also like, if there's privacy, payment protocols, etc., like the most of the stable coins, all of the stable coins more or less today that are centralized will not really touch privacy-based protocols. It's just not, it's a big compliance sort of issue. And so if we want more censorship-resistant kind of stable coins, serving both the UX of what users want, but also, yeah, like the like, the ability to transact in a much more private manner, like this could be really interesting. And again, it's also like a way to borrow against Bitcoin. And so there's like protocols that exist today, things like Liquidity V2, that could come on Bitcoin soon. And they would be able to launch with no upgradability, no governance, no added token, etc. Where you can, with smart contracts, stables that are fully backed by BTC, and take those stables into other applications like maybe shielded CSV, or even there's plenty. Like I think Fedimint is also really interesting, where we can try to go deploy some of those stable coins. So this is really unique, and I think it's worth highlighting. I mentioned Liquidity V2 here. The Liquidity team's done some great job on the Ethereum side. It's ETH-based stablecoins. Obviously, I think the BTC-based stablecoins even make more sense. And I think there's a strong distaste for algorithmic type of stablecoins, but this is a very different style of this design, and it's survived for a very long period of time across all the different volatility that we've seen in the underlying collateral. So yeah, I'll end it there if there are any more questions.
Yeah, Sebastian?
I wanted to ask you, do you have any general introduction material for SNARKS? We're interested in the topic.
Okay, sorry. Yeah, happy to provide. We have some materials on that for sure. And yeah, I'll follow up with the slides and some of those materials. Yeah.